one, we got a molecular formula came up with it. I mean, you should know how to do degree of saturations. But it probably doesn't need it because it's just a three carbon pair. So it's pretty small molecule. The things that you need to pick out is, first of all, there's a 3 line, right? We got 3 carbon, we got 3 line. So whatever that means is this is a same number of carbon pairs. So that means the molecule is not symmetrical. And then what this D key means, that letter next to the pig is telling us the splitting pattern. The one is shown is a decouple. So that's why it's a single peak for each carbon. But when you allow the splitting happen, then this is going to be turning to doublet, that's going to be turning to triplet, and that's going to be triplet. So that's the information to be useful for us to figure out how many hydrogen that particular carbon may have. This is a doublet because we expect that this carbon has just 1 hydrogen, right? So that's why it could turn into doublet. And then that being triplet means that this particular carbon should have a 2 hydrogen attached to that, and then same thing to the other one. Chemical shift is something that you should look at next. These 2 peaks appears in 140 and 115. So those 2 are appearing in a range where the double bond carbon shows or the benzene shows. But the thing is, this is just a 3 carbon, so there's no way this could be benzene. So this will be double bonds. So we know the double bond can have each carbon double bond has a maximum 2 hydrogen, right? So this one just having a 1 hydrogen, that one 2 hydrogen, so you can figure out what pieces that could be. And that one is a triplet appearing in the letter 65. And that is, if you should have a picture over there, that's going to be the aliphatic coverage carbon may not have the electron withdrawing group like oxygen. What can pull it down over 60 could be the oxygen. So this carbon should have oxygen. So what I would do, I would probably put the piece that I would think about for responding to this signal. There's a doublet on 140, so these should be double bonds with a 1 hydrogen. And there's a triplet in the 115, so that should be another double bond with the 2 hydrogens. And then this one's a CH2 because we got triplet there. And then biochemical shift over 60, I'm expecting it has the oxygen there. So once you get the pieces found out, then you need to make sure that you got everything there. First of all, the number of the carbon. 3 carbons, I have 1, 2, 3, so I have all the carbons. Do I have all the hydrogens? 6 hydrogen, I have to find out 1, 2, 3, 4, 5, 1 missing, but that hydrogen definitely can go to the oxygen there, right? And then all we need to do, just put it together. We found everything in the formula. So double bond should be close together, that should be making double bonds. And these open end must be connected to that open end, and then that should be the structure. So you can approach this NMR problem step-by-step manner, Pay attention to how many signals you're going to see there, where it's going to show, any of the information like integration for the total NMR, splitting, and this chromatography to this, this decoupled, this top spin coupling. Then you figure out what would be the structures for the portions of the molecule, and then you need to put them together to figure out what the overall structure should be. So anyway, that is not a typical one. The one below is a 4 carbon. The formula says 4 carbons. We got 1, 2, 3, 4. So apparently this molecule is also what I think having no symmetry. And now we need to think about the chemical shift. The single pair, singlet, showing 180. The 180 is a pretty visual division, right, downfield. That is clearly the carbonyl. I can think of that is a carbonyl. And then we got the triplet here on the 70 ppm, and 70 is I would expect that carbon bearing oxygen. So oxygen will bring that down deviated region like that. But those two is the one that doesn't have oxygen as a substituent, right? Because it's a kind of an upfield. So about turn into triplet if you allow them to couple, meaning that this is a carbon with the 2 hydrogen, that's the carbon with the 2 hydrogen, that's the carbon with the 2 hydrogen. So put it all together. This is a definitely carbonyl, right? It's a CH2 determined by the triplet when you allow the coupling. And then having an oxygen there by the chemical shift over 70 kind of indicate that that's the carbon with an oxygen. And then the other two is basically CH2, CH2. Now, you have to put them together. So I'm just connect this one there, that goes here, that goes here, that goes there, and that will make these structures. Will that be the correct structures showing that spectrum? I mean, first of all, finding pieces of the structures from the NMR spectrum, that takes time and that takes an effort. But if you're just so happy about it and just put them together and make the structure like this in a hurry, then you might get a wrong answer. There is a different way to combine these pieces together. So for instance, this goes there, but what about this goes here and that goes there, that goes here and that goes here? You know, there's many different combinations you can put it together. For instance, that one is one possible way, just connecting this way. Another way is that this goes to the oxygen and that goes all the way down and connect this way. The difference is where the oxygen is going to be in the structures. It's going to be here or it's going to be there. So how are we going to figure out which one is the right one and which was the wrong one? So that is something that you should do for double checking your answer. Let's say if this is the final structures, then do you expect this spectrum from the structures? That is how you check it, whether that's a right or wrong. So let me tell you what is the information that I can tell to narrow down the one choice. If this is a structures, you have this carbon having oxygens. So this is going to be visually showing between the 60 and 90 regions. So we got one pin. But that carbon also have an oxygen too. So I'm expecting this carbon also show the same region. In fact, this carbon having an oxygen here, carbon in there, so this carbon is going to be a little bit more distributed than that one. So we should have a 2 signal in the 60 to 100 regions. But I'm just only one. So having just one pig in these regions, meaning that we only have one carbon having oxygen there. The other 2 carbons don't have an oxygen as a substituent. So that is going to be how we're going to narrow down which one is the right one. So I know you get the pieces, you can get the pieces right, but if you're combining things wrong, then you get the wrong answers. So you want to make sure that you double check your answer by predicting what will be the NMR spectrum of your answer. So hopefully you can find whether that's going to match with the spectrum given, or maybe that's not going to match, then you have the wrong answer, then you have to figure out some other way to put them together. So this is the reason why this NMR question could be a little tricky, but that also makes it very powerful. We can tell the differences between these two. Right? That's why NMRs are useful to figuring out what is the structure of the molecule that you want to analyze. All right, so this is the right answer, that one.